Hello and welcome to another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson number 9 on rotations in the coordinate plane. Now, Unit 5 has all been about the coordinate plane and discovering and using the tools of the coordinate plane like midpoint, slope, distance, things like that. And we're going to continue to use them in the last 3 lessons of this unit. But the last 3 lessons kind of have a slightly different purpose than the first 8. Which is that we're going to go back and we're going to look at some of those transformations we did in Unit 2, but strictly in the coordinate plane. Now we did a little bit of that work in Unit 2, but we're going to get to it in a little bit more depth now that we're in Unit 5, and we've been devoting ourselves almost exclusively to work in the coordinate plane. Today, we're going to look at rotations, which are some of the harder ones to do in the coordinate plane, but we'll show you some tricks of the trade. We'll also tell you how you can kind of learn some rules about rotations, all right, and see where we go on that. So let's get into it now and take a look at the first exercise. All right, in exercise 1, let's take a look. In the diagram below, segment AB is shown with endpoints at A, 1, 5, and B, 7, -3. And it says draw A prime B prime, the image of AB, after a 90-degree counterclockwise rotation, a 90-degree counterclockwise, very important, rotation about the origin. State the coordinates of A prime and B prime below. All right, great. Now, there are definitely rules for rotations about the origin based on 90-degree increments, and those are the only kind you're going to have to worry about. 90-degree rotation, 180-degree rotation, etc. All right. Most of the time, the way that you can actually do these rotations is fairly simple and obvious. If I need to rotate this by 90 degrees about the origin, what I do is I simply click on my graph, or I just shove it off the page. Now, but what you'll do is you'll take your piece of graph paper and you will simply rotate it 90 degrees. All right. That is the easiest way to do it. All right, in which case you can literally now look at this point and where A is gone, and you can say, well, it's at -5, +1. Right? And you can also look at this point up here and you can say, oh, that's going to be at +3, +7. Right? Now, when you want to actually plot A prime, B prime, you simply rotate your graph paper back to the normal orientation and plot it. -5, +1, there's my A prime, and +3, +7, there's my B prime. All right, I really could use a ruler right now, but I don't have one. So I'm going to break out of here really fast and grab my ruler. All right. Go back into my full screen view and let's connect those 2 points. Just so that we've got our segment image. All right. Thank you, ruler. Maybe collapse you down. Store you over here. And there's A prime, B prime. Right? That's a little bit surprising because it may not look so much like it's been rotated by 90 degrees about the origin, counterclockwise, but it certainly has. Now, one of the things that we'd like to do throughout the next 3 lessons is loop back and be able to examine some of the properties of rigid body motions now using the tools of coordinate geometry. And again, those tools are primarily the slope formula, the distance formula, and the midpoint formula. So let's take a look at one very important property of rigid body motions, of which a rotation is, and that is what happens with lengths under rigid body motions. So in letter B it says, find the length of AB and of A prime B prime using the distance formula, okay, one of our tools that we've developed. Show your calculations. What observation can you make about their lengths? All right. Now, you should know the distance formula at this point. If not, this is going to become a problematic lesson for you. But what I'd like you to do is pause the video for a moment, and I'd like you to use the distance formula to find the distance between A and B, all right, and then between A prime and B prime. And remember, when we find that distance, we're finding the length of this line segment and the length of this line segment. So pause the video now and take a few minutes doing that. All right, let's go through it. All right, let me actually write down my A and B right here. Well, actually, I guess they're sitting there, so I'll be able to see them. I'm going to pan this up a little bit like that. Let's do the distance formula. All right, as a review, the distance formula really is just the Pythagorean theorem, right? We need to find the difference between the x coordinates and square it, the difference between the y coordinates and square it, add the two together, and then take the square root. In the case of AB, what that thing gives us is 7 minus 1 in terms of the x-coordinate differences, and negative 3 minus 5 in the case of the y-coordinates. All right, I'm going to very quickly run out of room, but I'm going to have 6 squared here. I'm going to have negative 8 squared there. All right, when I do all of that, I'll get the square root of 100, and that'll give me a length of 10. Okay, not too bad. Again, sorry about running out of room. Let's take a look at the length of A prime B prime. All right, I'm not going to rewrite the formula out. I'm just going to start to apply it now. I'm going to have to like squeeze it in here a little bit, but I think we can do it. So for A prime B prime, the difference in the x coordinates is 3 minus negative 5, which I need to square. And then the difference in the y coordinates is 7 minus 1, again squared. 3 minus negative 5 is going to be 8 squared. 7 minus 1, obviously 6 squared, which then gives us the square root of 100, and that's 10. What's the obvious observation then that you can make based on these two calculations? Let's do it. The observation is the rotation preserved the length of the segment. And that's one of the many reasons it's called a rigid body motion. Right? The whole idea of a rigid body motion, the whole idea is that the object that's being transformed doesn't change its shape or its size. And one of the primary properties of rigid body motions, all rigid body motions, is that they preserve the distance between 2 points that are being transformed, which then goes on to preserve the length of line segments. All right, let me kind of step back, let you copy some of this. Actually, let me kind of bring this up a bit so that you've also got the coordinate points in the graph there, and then we'll move on. All right, let's move on to the next problem. So again, each one of these exercises hopefully is going to illustrate another point in terms of rigid body motions that we saw before, and also help us use the tools of coordinate geometry. Let's see what we're doing in exercise number 2. For segment CD shown with C at negative 3, 8 and D at 9, 2, do the following. Find the image of CD, i.e. C prime D prime, after a rotation by 180 degrees counterclockwise about the origin. State the coordinates of its endpoints below. All right, well I kind of showed you the trick before, but what I'd like you to now do is try it on your own. In other words, take your graph paper and rotate it 180 degrees, a half of a full turn, around the origin, and try to determine then the coordinates of both points C and D, and then we'll take a look at the next part of the problem. All right, let's go through it. Now, to do a 180 degree rotation, right, you'll do a 90 degree rotation, followed up by another 90 degree rotation. What some of you might be wondering is whether or not it matters whether you rotate clockwise or counterclockwise. And with a 180 degree rotation, it certainly doesn't matter whatsoever, all right? But that's the only one. Well, I guess that and 360 and a few other specialty ones, but really the 180. So let's take a look. Right now we can read off the coordinates of really what will become C prime, and that's going to be at what? 3 and then negative 8. And of course we can read off the coordinates of D prime, which is going to be negative 9, negative 2. D prime, it doesn't really look like a D. Maybe make it look a little bit more like a D and less like an O that's having issues. All right. You might even notice something that hey look, it's the exact same coordinates. They've just had their signs changed, right? This was at negative 3, 8. This is now at 3, negative 8. This was at 9, 2. This is now at negative 9, negative 2. Let's actually do the plotting though. We haven't done that yet. And in order to do that, I need to rotate my graph paper back up to where it started. And let's now do 3, negative 8 for C prime. And let's do negative 9, negative 2 for D prime. I'm going to exit this really quick again and grab a ruler. All right, and let's draw the line segment. Always have your straight edge handy. All right, and there's C prime, D prime. All right, now we already know that it's going to preserve the length of the segment, but let's look at another interesting thing that we saw come up in Unit 2. Let's figure out what the slope of CD is and what the slope of C prime, D prime is, and compare them. All right, now you already know the slope formula, so yet again what I'd like you to do is try to find the slope between these 2 points and then the slope between these 2 points, and then we'll make a comparison. Why don't you go ahead and take some time to do that. All right, let's go through it. The slope formula. All right, we already reviewed the distance formula, but let's take a look at slope. Slope is the change in y divided by the change in x. That's y2 minus y1 divided by x2 minus x1. And we're going to start with these 2 points, right? So the slope of CD will be 2 minus 8, there's our change in y, and 9 minus, be careful here, negative 3. So that'll be negative 6 in the numerator and 12 in the denominator. Of course, 6/12 will reduce to 1/2, but we can't lose the negative. So the slope of CD is negative 1/2. And now let's do the slope of C prime, D prime. Maybe do this one in red so that we can kind of circle these two. All right, in this case, we'll skip right to the calculation. I'm going to have negative 2 minus negative 8 in the numerator. And I'm going to have negative 9 minus 3 in the denominator. That'll give me a positive 6 in the numerator and a negative 12 in the denominator. Now, as a little side note, previously we had a negative 6 divided by 12. Now we have 6 divided by negative 12. For some students who are still a little bit wondering about things like fractions, division, positives, and negatives, these two numbers may seem different to you. But keep in mind, really, that when you're looking at a fraction, all right, if you have a positive divided by a negative or a negative divided by a positive, your end result is negative, which is why I like to think about this not as negative 1 divided by 2 or 1 divided by negative 2, but simply as negative 1/2. Right? Likewise, this is also negative 1/2. And it's extremely important that you recognize that these two slopes are the same, that, you know, the fact that the negative showed up in the denominator here was just a product of which one we called x1, y1 and which one we called x1, or x2, y2. Sorry about that. Now, what must be true about these two segments based on that calculation? It must mean that they're parallel, right? The two segments are parallel. Now, I'm not going to make a claim right now that whenever you rotate a segment, you always get another segment that's parallel to it. I would never want to make that claim, because take a look at our last problem where we rotated 90 degrees, right? These two segments are most certainly not parallel to each other, given the fact that if we extend them indefinitely in both directions, they would certainly intersect, like right around there, okay? But one observation that we did see back in Unit 2 was that when we take a line and we rotate it by specifically 180 degrees about a point not on that line, i.e. we've taken this line segment, rotated it 180 degrees about the origin to get this line segment, then we get two line segments that are parallel. 180 degree rotations of lines about points not on the line give you parallel lines. Again, if you actually rotated a line by 180 degrees about a point on the line, it would just land on itself, and I hope that makes sense. I mean, that's just me saying, hey, if I have this and I twirl it 180 degrees about any point, it just kind of lands on itself. Anyhow, step back, take a look, copy down what you need to, and then we're moving on. Okay, let's do it. Exercise number 4. Now, a lot of times, teachers, perhaps even your teacher, will ask you to memorize the rules of rotation. Specifically, where does a particular point get mapped if you rotate it by 90 degrees counterclockwise, 180 degrees counterclockwise, 270 degrees, etc., etc. If your teacher asks you to memorize those, if you're good at memorizing things, they're not bad things to have. And oftentimes, even questions come up on a test, sort of like this one. Let's take a look. Exercise number 3. Which of the following represents a rotation of a point A, B by 90 degrees clockwise about the origin? Use of the grid is optional, but encouraged. All right. Now, in this case, what we're looking for is a general rule. How does this play out? And what I would always suggest in a situation like this is that you choose a specific point, one where the x and the y coordinates are different from each other. Don't choose the point 1, 1, 2, 2, 3, 3, or anything like that. Let's actually take, let's say, the point, I like 4, 2, right? The point 4, 2. And let's actually rotate that by 90 degrees clockwise and see where it ends up going. Now, for me, in order to do that, I've got to actually group these two together. Hey, why not actually take that all together? Let me group. All right, for you, you just put the dot on the sheet of paper and rotate it. Okay, I gotta be careful. And I need to rotate it clockwise 90 degrees. So where did the point 4, 2 end up? Well, it ended up at the point 2, -4. All right. Let's go back to there. So if we then had a point A, B, what exactly happens? Well, it looks like the two switch places, right? The 4, 2 became a 2, -4. So they switched places, and then what happened? Nothing really happened to this one, right? The 2 stayed a 2. On the other hand, the 4 got negated. So it appears like the general rule is B, -A, which is choice 4. All right? So if you're ever trying to discover or deduce a more generic rule, what is extremely useful is to take a specific point. Again, try to pick one where the x and y coordinates are not the same. All right? Otherwise, it can be deceptive. If I had 3, 3, that would then get mapped to 3, -3 under this rotation, and it would just be like, well, I don't know, the 3's, did they switch? Did they not switch? Here, you can see that the x and y coordinates both switched, and then that x coordinate got negated. Now, again, if it's worthwhile for you to memorize this rule so that every time you rotate by 90 degrees clockwise, you know that you switch the x and y and you negate what the x was, great. If not, then just do it with a test point. Okay, let's keep going. Now, the most challenging thing with rotations, bar none, is rotating about a point that isn't the origin. And yet, we know from past experience, questions like this come up on exams, standardized exams like the New York State Regents exam. So we'd like to get a little bit of practice with it, okay? And let's kind of talk about how to think about them. They're still not that bad, but they are most definitely more challenging than rotating about the origin. So in this particular problem, exercise number 4, it says, in the diagram shown, triangle ABC is drawn as well as point D. Letter A asks us to draw the image of ABC after a counterclockwise, always important on the direction, a counterclockwise rotation of 90 degrees about point D. State the coordinates of the image points. All right. Now, remember what a rotation truly is. It's really kind of like taking a point, like A, okay, connecting it to the center of rotation, and then rotating that in a circular way about that point. Now, my bet is you can already see what would happen to A, right? If A was rotated 90 degrees counterclockwise around D, what would happen is it would go down like this, and it would end up being, let's see, yep, it would end up being right there, okay? It would be exactly the same amount under D as it was to the left of D, because a rotation is just moving a point around a circle. All right? So in fact, it looks like A prime would end up being at 4, comma, -5. Right? Now that one's pretty easy because A is literally to the left of D by 8 units. So it's pretty easy to then just rotate it down to here. So how do we do it more generally? Well, for a minute, let me kind of get rid of all of that. And let's play the same trick that we did before, okay? I'm going to group these things together really quick so that they all come with me. All right. And if I rotated this 90 degrees, like that, counterclockwise, what I see, or what I want to pay attention to, is now not where A is compared to the origin, but where A is compared to D. And where A ends up landing is 8 units below D. That's the key, right? It's not compared to the origin. I don't care about the origin anymore. I care about point D. And the image of point A ends up being 8 units below D, right? So then I could always rotate it back and say, all right, well, it was 8 units below D. 1, 2, 3, 4, 5, 6, 7, 8, right? And I could do that and say, well, there's A prime, okay? So let's take a look at doing that with both point C, or point B and point C. For right now, I'm going to erase A prime because I don't want to have to regroup it. But let's just take a look for a minute where point B goes. All right, let me rotate this. Whoops, try one more time. Come on. There, thank you. Now again, where is the image of B, this point, compared to where D is? Well, it is 1, 2, 3, 4, 5. It's 5 units to the right of D, and it's 1, 2, 3, 4, 5, 6 units below D. So I'm going to just write that down. 5 right and 6 down. All right, now what I'm going to do is I'm going to rotate this back real quick. Well, I should probably get rid of this. I'll rotate it back, otherwise there's going to be a lot of mess on my board. Oop. Delete that. All right, so where would B have gone? B would have been 5 to the right, 1, 2, 3, 4, 5, and 6 down. 1, 2, 3, 4, 5, 6. So this is where B prime is going to be. And what are its coordinates? 9, -3. All right, I'm going to maybe eventually erase B, or maybe I'll leave it there and just group it with all the rest of them. Try that trick to find the image of C, in other words, C prime, after a rotation of 90 degrees counterclockwise about point D. All right, let's go through it. Again, what I'm going to do is move point B prime off of there. Lovely. I'm going to rotate 90 degrees counterclockwise. Now again, where is C compared to D? Well, C is now 4 units to the right and 4 units up. So it's going to be 4 right and 4 up from point D. All right, because remember, under a rotation about point D is not going to go anywhere. It's like I'm holding my paper down at point D and I'm spinning it around it, right? So now, as I spin it back, right, then I could say to myself, all right, well, that's kind of fun. I can go 4 to the right and 4 up, and I will be right here. Okay, I think I'm now going to erase that. So there's my C prime, which is at 8, comma 7. Okay, so might as well move my b prime back. Well, that didn't work. Actually, might as well just put it back on there. 9 comma negative 3. And I still don't have a ruler. All right. Must remember to bring my ruler to class next time. Okay, let's connect them. I lost my a prime. Where did it go? Anyway, we're going to go 4, negative 5. There's my a prime. Okay, let me connect them all. Why don't you go ahead and do the same? It's quiet work. All right. Bouncy ruler. Okay, there we go. We've rotated ABC by 90 degrees counterclockwise about point D. And again, it's much harder because you can't read off the coordinates of the points as you rotate about that point, not the origin. But what you can do is sort of read off their coordinates relative to point D, right? Because these are kind of like coordinates, right? We would have normally said, oh, it's 5 right, 6 down from the origin, but then that would have been just 5 comma negative 6. On the other hand, here it's 5 right, 6 down from point D, all right? Now, letter B says, verify using tracing paper that triangle ABC is congruent to triangle A prime, B prime, C prime. Remember, one of the definitions of congruence is that there is a rigid body motion that maps one figure onto the other. So what that means is that when we actually do rotate a figure like a triangle about a point, any point, then the triangle that's produced should be identical to the original. So let's take a look, right? Here we've got this beautiful traced out triangle, and I want to see if that lies on top of here. Now, of course, in order to make it lie on top of there, I very well may have to rotate it some, right? And in fact, if I rotate it 90 degrees, it lies right on top of it. All right? And again, one thing that's nice about that is it shows you at least by the use of tracing paper that you actually did do a rigid body motion. Did you do it in the right direction? All of that, that's more questionable. But it certainly is a rigid body motion because it didn't change the shape or the size of our original triangle. All right, let me kind of cut out of the way for a second, let you take a look at these, and then we'll move on to the last problem. All right, let's do it. Last problem. All right, again, a rotation about a point other than the origin. Let's take a look. Exercise number 5. If the point A, negative 3, 7, is rotated 180 degrees clockwise around the point B, 2 comma negative 5, the image would fall on which of the following points? All right, I'd like you to take a little bit of time and think about this. There's a little bit of a tricky nature to this problem, but I think with a little bit of thought, that can actually be a good thing. So go ahead and work on it a bit. All right, let's go through it. Now, a little bit weird, right? So I've got negative 3, 7. That's my point A. And I've got the point 2 comma negative 5. That's my point B, right? And I want to rotate A by 180 degrees about B. All right? Now, even if I kind of group these together, yep. Even if I group all of these things together, I'm not actually getting this graph in there. Oh well. If I do that rotation, hopefully you can see that A will end up falling off the graph paper. It'll be somewhere down here, right? If I rotate this 180 degrees, A prime is going to be down there, all right? So how can I do this? Seems a little unfair, like they gave me graph paper that was way too small, okay? Except there's something that's very nice about 180-degree rotations. Yeah, you know, it takes lines and maps them to parallel lines. But the great thing about 180-degree rotation is that when I take A and I rotate it 180 degrees about B, its image, A prime, along with B and A, are all collinear. They all must fall in a straight line. Now here's why that's important, right? We know that the distance from A to B has to be the same as the distance from B to A prime because it's a rigid body motion, right? So that distance and that distance can't change. But even better yet, because it's collinear, what that means is that if I kind of look at this and I say, well, you know, to go from here to here, right, would be 5 units, and then to go down to here, it would be, what? It would be 12 units? 5, yeah, it would be 12 units. Yes, it's almost kind of a little bit of a slope calculation. Then, likewise, right, to get down to A prime from B, you'd have to go 5 to the right and another 12 units down. So what would that be, right? If I take the coordinate point B, 2, -5, and I sort of go 5 to the right and 12 down, right? Well, 5 to the right, you just add 5 to the x-coordinate. 12 down, you would just subtract 12 from the y-coordinate. And that looks like my image point is going to be at 7, -17. Choice 1. All right. Now again, we can do that because it's a 180-degree rotation. And 180-degree rotations are amazingly important. The 3 points, the pre-image point, the point of rotation, and then the image point are all collinear with one another. Oh wow, my Dropbox is almost full. Great. I'm not going to upgrade right now, Dropbox. We'll take care of you later. All right, let's get back to this. Okay, let's wrap up this lesson. All right, and then we'll get rid of the Dropbox notice. Love Dropbox. So in today's lesson, what we did is we looked at different rotations, right? We looked at rotations about the origin and about other points, and we specifically kept them in increments of 90 degrees. If you're worried about what you would do with a 60-degree rotation, a 30-degree rotation, things like that in the coordinate plane, you don't have anything to worry about right now, okay? Right now at least. Those are very challenging rotations, and they actually involve more mathematics than what we have at our disposal right now. Eventually we would have enough to do it in this course, although what we'll be sticking with in the coordinate plane are only rotations by 90 degrees. That's it, okay? Or 90-degree increments. Okay, in the next few lessons we're going to see things like translations and reflections in the coordinate plane, and we'll be using those tools of coordinate geometry, the midpoint, the slope, and the distance formula, to actually look at all of them. All right, let me thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.